Welcome to the Explainer. Today, we're basically becoming cosmic detectives. We're going to try and answer one of the biggest questions humanity has ever asked. In all this vastness of space, how in the world do we find another Earth?
All right, let's just dive right in. When you look up at that glittering night sky, you're only seeing a tiny, tiny fraction of the hundreds of billions of stars in our galaxy. So faced with this just unimaginable cosmic haystack, the first big problem is simple. Where do you even start looking?
To keep from just getting totally lost in that sea of stars, astronomers don't just point their telescopes at random. Nope, they act like real detectives, using a whole series of clever filters to narrow down the suspects and hone in on the stars most likely to be hiding a planet just like ours.
So what's filter number one? Well, it all comes down to the ingredients. Because think about it, just like baking a cake, if you want to build a rocky planet like Earth, you've got to have the right cosmic materials there from the very beginning.
You see, stars and planets, they're born from these huge, swirling clouds of gas and dust. Now, for a system to even have a shot at forming rocky planets, that cloud has to have enough heavy elements. And by that, I mean everything heavier than hydrogen and helium, which astronomers, well, they just group them all together and call them metals.
I'm talking about carbon, oxygen, silicon, iron, the actual building blocks you need for rocky planets. And, let's face it, for life as we know it. In our own solar system, these so-called metals make up about 2% of everything. And that number, that gives us a huge clue, like a cosmic fingerprint to look for out there.
Now you might be thinking, that's a pretty strict requirement, but here's the surprising part. It's not. Turns out most of the stars in the Milky Way, especially the younger ones like our Sun, are metal-rich enough to make the cut. So yeah, it's a vital first step, but we definitely need a stronger filter to really narrow down our search.
Okay, our next filter is all about time. It took billions of years for complex life to show up here on Earth. So if we're hunting for another Earth, we need to find a star that can provide a stable, long-lasting home. We're talking billions and billions of years of stability.
So astronomers classify stars by their temperature and size into these spectral types. You can see them here, from O all the way down to M. Now I want you to look at that lifetime column. See those massive O-type stars at the top? They're like the rock stars of the cosmos. They live fast, they burn incredibly bright, and they die young, flaming out in just a few 100,000 years. That's just a blink of an eye, nowhere near enough time for life to get a foothold.
So right off the bat, we can just cross those massive, brilliant O and B stars off our list. They're just way too short-lived. This leaves us with the smaller, cooler, and much, much longer-lasting G, K, and M-type stars. These are our prime suspects. You could call them our Goldilocks stars. Not too hot, not too short-lived, but just right for a world with life.
And get this, here's where things get really interesting. This chart shows you just how common each type of star is. And our prime suspects, those long-lived, cooler stars, they also happen to be the most common stars in the galaxy by a long shot. Just look at the M-class stars. They make up a whopping 76% of the total.
So when you add them all up, these G, K, and M-class stars, they account for something like 97% of all the stars in our galaxy. Just think about what that means for a second. It means that almost every star out there has a long enough lifespan to potentially host a world where life could evolve. All of a sudden, our odds are looking pretty darn good.
Okay, so we've sifted through the stars. We know where to look. But the next big question is, how do we actually find the planets? Well, the answer is just fascinating. It's all about looking for the tiny, subtle gravitational tug that an orbiting planet has on its star.
Trying to directly see a tiny, dim planet against the incredible glare of its star is, well, it's pretty much impossible. It really is like trying to spot a firefly right next to a giant searchlight from miles and miles away. So, since we can't see the planet directly, scientists had to come up with some truly ingenious indirect ways to find them.
Okay, so here's the cool part. A planet doesn't just orbit its star. They actually both orbit a shared center of mass. Now, because the star is so much bigger, that point is super close to the star, but it's not at its dead center. And what that means is the star doesn't sit perfectly still. It actually wobbles in a tiny little circle. It's kind of like two dancers of different sizes spinning around together. Now, we can't actually see this tiny wobble from light years away, but, and this is the clever bit, we can detect the effect of that wobble on the star's light. The technique they use for this is called the Doppler method, and it works by looking for tiny, repeating changes in the color of the light that we get from that star.
It works on the exact same principle as a train whistle.
You know how as a train comes toward you, the sound waves get squished together and the pitch sounds higher? And as it moves away, the waves stretch out and the pitch gets lower. Well, the exact same thing happens with light. As the star wobbles towards us, its light shifts a little bit blue. And as it wobbles away, it shifts a little bit red.
And when you plot that data over time, you get this. By precisely measuring those tiny shifts between red and blue, astronomers can create this velocity curve. This beautiful, repeating wave. That's the telltale signature, the smoking gun that reveals an unseen planet's gravitational pull. And from this pattern, they can figure out the planet's mass and how long its year is. It's amazing.
Okay, so the wobble method is genius. But there's another technique that has been even more successful. This one relies on a bit of cosmic luck, a perfect alignment from our point of view that lets us watch a distant planet create its own tiny repeating eclipse.
Now there's a catch. For this method to work, the planetary system has to be lined up perfectly edge-on from where we're watching here on Earth. And that's just pure chance. It only happens for about 1% of star systems out there.
But when we do get lucky and the alignment is just right, this is what we see. It's called the transit method. As a planet passes directly in front of its star, it blocks a tiny, minuscule amount of starlight, and that causes a very slight but measurable and, crucially, periodic dip in the star's brightness. You can see it right there in that light curve.
So the process itself is simple, but it's incredibly powerful. Telescopes, like the famous Kepler Space Telescope, they just stare at thousands of stars at once, constantly measuring how bright they are. When they see one of these tiny, repeating dips, a dip that happens on a very regular schedule, boom, they know they found a planet.
So, how well have these cosmic detective tricks worked? The answer? Incredibly well. Combining the Doppler and transit methods, scientists have now confirmed the existence of thousands of planets orbiting other stars.
I mean, just let that sink in for a second. In just a couple of decades, we have gone from wondering if there were any other planets out there at all, to knowing for a fact that they are common. We've figured out how to filter the cosmos, we've learned how to see the invisible, and we've confirmed that our galaxy is just teeming with new worlds.
And that leaves us right here, on the edge of the ultimate question, doesn't it? It's the challenge that's going to define the next great frontier of astronomy. We've proven we can find these thousands of new worlds. So now, how do we search them for signs of life?